Thank you all for coming tonight. My name is Tristan Blake. I'm the founder of the Machine Learning Society, and it's our mission here to establish a collaborative data science and artificial intelligence community in San Diego. Judging by the turnout of this event, I think we're off to a great start. By hosting workshops, panel discussions, Kaggle competitions, and even hikes for computational scientists and data scientists, we aim to engage, educate, and inspire our members to push the boundaries of artificial intelligence research and business applications. For those in the audience that have attended our previous events, welcome back, friends. For those of you that come for the first time, welcome home. We host weekly events that enable our members to think of new and exciting ways to apply data science, machine learning, and computational science to global challenges. Now, a few words about what makes tonight a very special event. Greg Scantlen and Rob Farber have conspired to challenge your conceptions of high-performance computing. We will unveil an open source architecture which reduces the processing time for a variety of scientific simulations from several days to several hours, and they will show exactly how they did it. Another special aspect of this workshop is the audience itself. In the last hour of networking, I had the opportunity to exchange ideas with world-class physicists, chemists, bioinformaticists, and data scientists, and mathematicians. This variety of domain expertise cannot be overlooked, and it is my personal opinion that it is this cross-disciplinary culture is what makes San Diego such a powerful scientific center. Now, allow me to share with you some of my personal ambitions for San Diego. You see, I'm not a scientist, nor am I a particularly good programmer or a data scientist. I studied history and political science, as I mentioned in a conversation earlier today. But despite not having a technical or scientific background, I am equipped to identify political and social phenomena. And if my training serves me correctly, something incredible is happening right here in San Diego. And every person in this audience is responsible for this transformation. San Diego is rapidly becoming a high-tech economy with an explicit focus on artificial intelligence startups and leading life science companies. It seems appropriate to rebrand San Diego with the following slogan: come for the beaches, stay for the business climate. Everyone needs to repeat that and remember it. Come for the beaches, stay for the business climate, right? This is the new San Diego. So I'd like to announce that the Machine Learning Society will host in December of this year the first ever data science, machine learning, and bioinformatics career fair in South California's history. This will be essentially our American Idol moment, and I wish to enroll all of you in helping make this career fair capture the world's attention and imagination. If we work together, we can bring talent, capital, and opportunity to our city. And achieving this dream is it does not require a wish or patience, but a formula with a strategy. A special thanks to SDSC for hosting us tonight. The San Diego Supercomputer Center is the jewel of San Diego's computational community. So let us give them a round of applause, please. We will open tonight's event with our sponsor, Bright Computing, that has graciously supported our community with food, drinks, and covering many of the event costs. Without them, tonight would not have been possible. In fact, Bright Computing's technology is so cool that I am actually structuring a follow-up event to deep dive into their cluster management technology, which is deployed across the world's largest research centers. But I will allow Lionel Gibbons to tell you a little bit more about that, so please come to the stage.
Computing. I work at Bright Computing. What Bright does is cluster management software. May or may not be of interest to you. So If you're a scientist and you're using clustered computers, usually there's two routes. Either the folks in your organization, whether it's an enterprise or an enterprise, you might have somebody taking care of the cluster for you, and then a lot of the work is taken on your hands. If you're an IT person, or if you wind up working with an IT person and have ever had to manage a cluster, build, deploy, manage, and upkeep a cluster, you realize it's a heck of a lot of work. It takes up a lot of your time. And what we find is a lot of research scientists that don't have their own IT staff, they wind up having to do it themselves. And it takes up so much time from what they love to do, their data science, their research, whatever it is. So Bright Computing was actually founded by researchers, guys that were scientists that said there's got to be a better way. And it's essentially a management platform.
Magic.
Okay. Well, I started to say this. Why Bright? This is a more succinct way of saying what I was just starting to say. We exist because clusters are hard. They're hard things to manage. If you have to manage a cluster yourself, this is I think the slide that I was on in my head, you realize how much work it is. It's a lot of work, takes a lot of time, and it's really a thankless job. And if you don't have an IT department and you have to do it yourself, it takes up a lot of time, and it takes away from your real work. So this is our official mission statement, but I like to put it this way. What we do is we make clusters easy. I'm the marketing guy. I actually wrote the other one, but I like this one. So where does this start? It all starts with workloads. A typical data center has all kinds of workloads. It could be HPC, could be big data, it could be machine learning, deep learning these days, or they could be running natively on the cluster, or they could be running in a container. Typically, these are Linux clusters, a bunch of Linux servers, generic Linux servers, running various bits of software networked together into a cluster. Not an easy thing to build. So what we do is we make that easy. So we use Bright Cluster Manager, we put these little demons in all of the nodes, and they basically help us manage the cluster. They keep an eye on the cluster, they do health checks, they let us talk to each machine in the cluster, and they let the cluster present as a single entity. So it's easier to manage. But that's part of the story. As you can see, the rest of it sits up on top of that. The workloads also have their own frameworks. If you're running HPC jobs, you're submitting them through workload managers. If you're running big data, you're probably running Hadoop or Spark or something like that. If you're running deep learning or machine learning, you're probably running a framework like TensorFlow, or Caffe, or something like that. All of these frameworks themselves are a pain in the butt to manage and configure. So we extended Bright Cluster Manager to manage those as well. So we make it easy to mix workloads on the same cluster. Not always something that's easy to do. So what happens is typically you will assign nodes to a certain task. Those first three nodes are running HPC and those ones are running big data. But what if the workload changes? We're running jobs where we've got to do a big data job and we need a lot of processing. We're not doing much HPC. If we're doing machine learning, we're doing more appropriate here. You can reassign the nodes in the cluster to be something else. So you can do it manually, or you can have Bright monitor the workloads in the frameworks and reallocate the workload dynamically. So now those 4 nodes are running big data, those 4 nodes are running machine learning. And then different time of the year, different part of the semester, you decide you need to do a lot of HPC. Same cluster, you reconfigure the nodes, and most of them are running HPC and none of them are running big data. Push of a button for us. Eventually you run out of capacity perhaps, so you can burst to the cloud. The nice thing is that the nodes that are running in the cloud, the virtual machines that are running in the cloud are running the exact same image as the ones that are running in your data center. So they're running the same image, the same daemons, same management interface. Oh, closer to, okay. When they're virtualized, we have this feature called cluster on demand, which could be of interest. If you're running an IT department, you can spin up a cluster and assign it to somebody. You can assign it to the physics department for a week, or you can assign it to the math department for a day. Spin up the clusters, they can run whatever they want on it. You still have control over it, but they have their own cluster. But you're paying the price of virtualization. So what if you don't want to? OpenStack has this cool thing called Ironic, which lets you do the same thing, but with physical nodes. So you can spin up these subclusters, if you will, using physical nodes, hand them off to somebody to use for a while, and then take those machines back and repurpose them. It's really cool. And this is all the stuff that we said that you could do in a physical cluster, you can do in the cloud. Reassign the nodes, distribute workloads, etc. etc. And you can see this building, right? Remember we started right down here? All of those nodes can be expanded into the public cloud if you want to capacity. And the nice thing is the nodes in the cloud, in the public cloud, the number of nodes you have scales. So as your demand goes up, we'll spin up more nodes. If demand goes down, we'll spin them down so you're not paying the fees to AWS. Right? And if the demand goes down enough, we'll even shut down physical nodes. That saves you power, saves you money. The biggest cost in a data center is power. And if the demand goes back up, we'll recommission the node, re-provision it, and put it back in the cluster. But because I had 6 minutes to do this without the part in the beginning, that's all I'm going to say. That's all I had to say was to show you what we do. If you're using a cluster, we can make your life easier. And now we'll just get on with the rest of the show.
So, my name is Greg Scantlen. I am CEO of Creative C, and we build custom high-performance computing systems. Our mission is to facilitate science and engineering. We do that by computing faster. In fact, I think our largest GPU cluster is in Los Alamos. It's 60 GPUs in one cluster, and it's managed by Bright Computing. Yeah. So, isn't that interesting? So we have an office in Albuquerque and an office in Los Alamos, and we work directly with scientists, and so we do a lot of custom tweaking. And so out of the conventional systems that I've been building for many years, in fact, one of our customers from way back is Rob Farber, who was a scientist in Los Alamos. And anyway, so Rob and I have a long history. So we've even changed our name. I mean, you can tell that Tristan's pretty enthusiastic about making all this work, right? So the new name for my system is Simul8, okay? Which I think that's okay because we're using a Power 8 processor from IBM, so why not simulate? But simulation systems are what we do, and simulation systems for science is our specialty. So I have many colleagues here today, and it's so nice to be in this environment. It's just great. Anyway, so if you're from New Mexico, you know it's neither. It's not new and it's not Mexico. So I know a few people from New Mexico would laugh about that. Okay. Okay. So long history with Rob Farber. Sean McKinney actually set this up, so thank you, Sean. He also, in the last 48 hours, has learned everything about NVLink and Jarvis. So when we have the meetup later, if you'd like to talk to Sean, he has some interesting things he can show you about NVLink and Jarvis. Tim Thomas, I've worked with him for years. Where are you, Tim? Oh, there's Tim back there. We have a LAMPS shock simulation that was done in conjunction with some scientists from Los Alamos. And Tim can show you a visualization of a 7 million atom shock simulation if you want. You can see every atom. Okay, it's about 10 nanoseconds long or something. Takes quite a bit longer on the computer though. Tim, okay, so Tim Andre does everything. Well, yeah. Andre's a consultant for Creative C on several grants and on a contract at Los Alamos where we maintain a fairly large cluster for materials science laboratory. And, well, we'll talk about that later. Gary Scantlen happens to be my brother. And I wanted to introduce Linton Ward, who's here from IBM. And Linton knows quite a bit about the IBM system that is part of our latest development effort. So we've been doing this quite a while. In fact, I don't know if you remember this, Rob, but just over 10 years ago. Yeah.
10 years.
It's been that long. Yes, Rob Farber called Creative C and said, you know, there's this new beta release of CUDA, and I really think you should check this out. So, you know, a few years later, Actually, my brother put together this simulation, and this is 12 GPUs doing 786,000 threads, recorded on my cell phone, in 2010. So that's cell phone resolution 2010. This is the table of contents here for the talk. I'm going to try to be brief on history, some instrument evolution that we've gone through. There is sort of a general strategy with our company that we can help you develop an instrument by co-design, right? So we can take the latest technologies, we build small, it's like a miniature data center. You can figure out what technologies you need, and that can evolve into an instrument for a particular type of simulation that you'd like to do. This machine is about to become the VASP instrument next month. We have a $70,000 grant from the state of New Mexico, and that will fund a scientist to do his work on this machine. And the purpose of all of this is hopefully to find other scientists that have work that they would like to co-design. We look to make simulations run faster, sometimes 8 to 10 times faster. For a scientist, if you're spending 2 weeks waiting for results, maybe you get those in 2 days. But the development platform, now the Simul8 development platform, is intended to help you create an instrument or learn how to scale up to make a larger cluster, have an idea of the best parts to use and the best way to spend your money when you go to scale up. So in 2010, we sort of came to this realization that there's this huge gap between a high-performance workstation and a building full of computers. And we feel that we sort of fit in that gap, and you can see things have evolved a little. This was running LAMPS. At a LAMPS conference, we were doing 3D visualizations back in 2010. We have had a commercialization where we've been the OEM for another company, so it's something you can think about. We've serviced 30 customers in about 3 years. We have these boxes all over the world. They're at universities, they're at Fortune 500 companies. A lot of national universities, Peru, Greece. There's several in France. And we're going to upgrade one at the New Mexico State University. Sorry, that's yes, right, they're here. Okay, that's Tim Thomas. And this is a booth that we did at GPU Technology Conference in 2014. And this is where the philosophy, I think, really sort of set that, you could have this sort of larger machine with more parts, and you could use that machine to figure out scaling, or you could evolve it into an instrument. And you can't see this too well, but this machine could actually have 8 GPUs. This more likely would have 4. But we can use various motherboards and components to really tune the machine to your workload. And lots of monitoring going on here, which after the talks, if you want, we have a few monitors set up, and we can show you lots of details on how the machines work. So Rob and I have been doing this for a while. This is Supercomputing 14, and there's Rob. I'm in Santa Fe. I'm sorry, this is something that happened in Berkeley, but okay, the picture is from Berkeley, but the event was in Santa Fe, excuse me. And that was Rob and I.
Supercomputing, that's C14.
Yeah, this is
That's the tutorial I
Supercomputing.
did.
Right, but this, I believe, was in Santa Fe, New Mexico.
Yeah.
Yeah, so anyway, we've done quite a few of these talks, and always been...
Greg's a great roadie.
Okay, next slide. Okay, DOE SBIR call. So, a scientist friend of mine a couple of years ago sent me this offer, for submission for a grant. And I think this is interesting, developing turnkey HPC appliances. DOE knows that, this is an area that needs to be filled. And so we did a submission, and Tim Thomas and I were funded $146,000 and we built an instrument called the LAMPS instrument. Right now, we're in second review because of the changing administration, but we have a grant for $990,000, which I really expect we're going to get. Okay, so many disruptive technologies. If you think about, actually this, I should say, this is from Alinea. It's called Performance Reports, and I think it's a very succinct way to sort of profile an environment. But what I like is they have compute, I/O, and memory. And those are sort of the three independent factors that you want to look at when you're trying to tune a system. If you look in all of those areas, there are tremendous disruptive technologies that are available. And how do you figure out which ones do you need, which ones do you not need, where's your advantage? And my contention is that you want to do that by bottom-up engineering, not by top-down. Instead of building a big system, build a small system, co-design it, get the best time to solution that you can, because that's really the best measure of performance, right? So open power is wide open. So GPUs are great for doing simulation, machine learning, analytics, right? So there is an online catalog of GPU accelerated applications from NVIDIA. I was on page 17 and 26. There are 5 pages that involve some sort of bioinformatics, biosimulations, many different programs. All of these programs, they can give you some idea of the speedups that you'll get, and this is on the last generation of GPU computing, not on open power, which is the next generation. And all of those different components have increased in capability significantly. So compute, I/O, memory, they're all faster. So there's a huge opportunity here, and there's even sort of a game plan on how you would look to speed up the work that you're doing. So the current grant that we're working on, that this machine is aimed at, is to be a VASP instrument. VASP happens to be number 6 user at Oak Ridge. I mean, this is a very large supercomputer. A lot of people are doing VASP. In Oregon, the supercomputer there is, 50% of the time is spent in atomic scale simulations. So VASP has a killer app. So we're working with the scientists. We've been funded by the state of New Mexico. We have $70,000 of his time unburdened, which is probably 2 or 3 months. When he submits his simulation at an institutional system, he gets in a queue and he gets 8 hours, okay? VASP happens to be a really, really compute-intensive application, and Andre will show you, we'll run VASP, and the machine will heat up, and we have this special cooling, you'll see bubbles. We can talk about the details of that later if you like.
Greg, I do like that we have to have you on the microphone with the machine running so we can hear you. So the machine's not so loud.
Oh, sure.
How quiet it is.
Oh, I'll go with it. Okay. So, because the simulation often exceeds, how's that? You can still hear me?
Yeah, it's not loud.
Okay, isn't that amazing? Okay. Because the simulation often exceeds wall time, you have to checkpoint, which means you have to save the simulation, right? Because it's very weak scaling, you can only use a few nodes. And Rob is going to tell you about strong scaling. Anyway, so it's difficult to save because it's a quantum chemistry simulation. So what happens is you wait in line for another week, you get 8 hours, but you're not starting where you left off. You're starting halfway where you left off.
So, Greg, would you be able to describe what VASP is?
Sorry.
Just a brief.
Sure. So VASP is a quantum chemistry simulation package. The V stands for Vienna. It was created in Vienna probably 3 or 4 decades ago. Correct me if I'm wrong. But it probably occupies 10 to 20% of all the supercomputer time at all the national labs in the US. Because it doesn't scale well, you can't use a lot of nodes. Okay, so you end up with a tremendous number of jobs running at once. And that was the slide from Oak Ridge. Okay, so the simulations that are being done in Los Alamos have to do with national security. Okay, they're experiments that you would not want to do in the lab. Does that make sense? So my contention is that open-powered VASP could outperform many large clusters. If we can make one very dense node that's 10 times as fast as a common node, you can't scale to do the job faster. Okay? If you're in the situation where you only get 8 hours of compute time, even though it's on a large system, per week, what we're going to do is we're going to try to build a machine, run it for 3 or 4 days straight, let it finish its simulation, and do as much work as a scientist would do in a month. We're trying to do it in a few days. And that is the purpose of this development. And the purpose of this talk is to let you think about maybe doing the same thing in simulations that you think are impossible because they'll take too long. Or simulations that change the workflow, the work that you think that you can do because it takes too long. So it's really about faster time to solution, computing faster. Okay, so yeah, I just wanted to announce that we have the $70,000 in funding. That's kind of a big for us. Thank you. So.
Testing.
Okay, so the theory behind the system, the way the parts fit together, is that we build a small data center. Okay, so the center, the light green node, is a head node, it's a visualization node, it's a storage node. Those are the functions that you would find in a large data center that we integrate into the center node. The yellow nodes are compute nodes. And in this case, we've taken a system from a data center, it was designed for a data center, and we've modified it, working with another company from Wisconsin. Their name is Ebullient. They have very special cooling capability, and we can talk about the details of that afterwards. But by using 2 compute nodes, you create a cluster, and that gives you the capability of building a software stack that will scale as far as you want to scale, as far as adding more nodes. And you can get enough experience from building this to know that your software will work, to know what kind of performance you're going to get out of these new disruptive technologies. And if you want, you can just keep scaling up from 2. So now we're calling this the Simul8 platform, and hope to talk to any of you that are interested in the strategy. Oh, how'd that get in there? You know what? Somebody turned on something. Sorry. Yeah, I think we'll stop there. And I'll introduce Rob Farber. Thank you.
Hi,
Sure.
So I want to thank Creative Consultants and Greg and team because they're the ones who actually flew me out. It's wonderful to be in San Diego again. I love the climate out here and of course the people. So it's appropriate. This is kind of the marketing slide that I have. Because Tristan is right. My favorite observation is that it took 500,000 scientists and engineers and 1 social media genius to send a man to the moon. And it really is in terms of communication and marketing that that we actually get the message out for people. Linus Torvalds changed the world in his dorm room by writing a new version of an operating system. But if he didn't get it out and get the word out through the internet, the Linux operating system wouldn't have gone anywhere. So the message that I always put into all of my presentations with marketing students and other people is that you need to learn to communicate and to get your information out, because otherwise the best work in the world doesn't work. So in fact, we eat our own dog food. So I have a couple books out on CUDA, the latest one on OpenACC. Both of these went into Chinese translation within the first week of being in bookshelves in the US. The kind of star spangle there, different places I've had the pleasure of teaching and giving talks, and then a number of different companies that I work with. And the topic we'll all be talking with you about is state-of-the-art machine learning and the near-term technology trends. There's a lot of material in here and a lot that I'll be skipping. This was actually an over-2-hour talk that I gave initially at Princeton, and then I give briefings on this for a number of other students as well. And I condensed this down to be about a half hour here. So please feel free to ask any questions. So in talking with people, I think I hit the right areas. That what we saw is a resurgence of parallelism, basically from games to supercomputers and now to deep learning. So this all started out about 2009 when NVIDIA and a company called ATI were fighting back and forth trying to capture the multi-billion-dollar gaming market space. And I love cartoons, it really gets the message across. And so then NVIDIA came up with the idea that, oh, we can program with this thing called CUDA and OpenCL. And ATI said, no, we don't need to develop our own language, we'll use OpenCL. And we'll work with that. And along the way, ATI became AMD, that you all are fairly familiar with. And the whole reason that we started moving to GPUs for compute is that CPUs, which everybody used up to that point in time, we had a failure of dense scaling loss, which means that people could no longer buy a computer that would run at a faster clock rate, and so they couldn't get that 2 or 4 times performance boost. It essentially created the rebirth of parallelism. We had massive parallelism on GPUs, and we had many-core parallelism on CPUs. So Intel kind of got interested in this. They looked over on the side and went, well, yeah, it's only a gaming market space. We don't play games, we do real compute. Then sales got to 100 million GPUs. And, well, then they kind of went, no, we're trying to wake up, but it's Larry there. Back to sleep again, okay? Well, then sales hit 500 million plus GPUs. And, it kind of woke them up. And so suddenly we now have a new computational workspace for HPC and for machine learning, where we have GPUs and we have Intel Xeon Phi. And so that's the new Knights Landing and the forthcoming Knights Mill coming along the way. So I'm going to talk to you about the different architectural differences before we delve into machine learning, so you can kind of understand the important distinctions between GPUs and CPUs. Because we've all heard about CUDA cores and massive parallelism, and CPUs may use the term many-core parallelism. So what is the genesis of this? Well, for GPUs, and actually for vector processing nowadays, the big hardware idea is called SIMD, single instruction, multiple data. And it started with the connection machine, which you have been around long enough, I actually ran with that, and that's where I did the mapping for machine learning that I'll tell you about today. And that was a 60 gigaflop machine. We have the Pascal P100, which is about a 5 teraflop single precision machine. So what we went is from a $30 million price tag to, here are some actual results showing Intel Xeon Phi and GPUs for 1 to 3K, and we're able to break the teraflop per second barrier with this. And here I'm showing you a result, showing scaling results of 16,384 GPUs for training, machine learning training. This is done at the Oak Ridge Titan, on the Oak Ridge Titan supercomputer, and we're doing actually 13 petaflops average sustained training performance. So the point is that for training with on machine learning problems, you can think big. You can think really, really big. And by the way, along the lines, you run into some interesting data problems. So what is this mapping that I told you about that I created way back when in the 80s? Well, it's a general mapping where you have effectively an optimization method. Powell conjugate gradient, whatever your favorite flavor of nonlinear optimization package is. And then we essentially have 3 steps to do each step of the machine learning training. The first is that you do a global broadcast of the model parameters for a neural network, and I'll go into this in a little more detail in the other slide. Well, if you think of the television broadcast model, that's the fastest way to get data inside of a computer architecture, because if you think of the television, it takes the same amount of time to broadcast to 1 billion television sets as it takes to broadcast to 1. So that basically goes in oaths of constant time. Then the next step is that it's completely strong scaling, because what we're doing is a least mean squares error optimization. So for every example in the training set, each one of the GPUs in this case, or it could be a Knight's Landing, or it could be your CPU, whatever it is, they're all independently calculating the partial errors. And so that's 100% strong scaling. You can run, if you've got 10,000 machines, you'll run 10,000 times faster. If you have 1,000,000 machines, you'll run 1,000,000 times faster. But then we run into the log growth, which is the reduction. And what we have to do is we have to get a single number back, which is the error that goes back, that the optimization method runs. So if we go back and do this in full speed now, and if you look over on the right-hand side, you can see actually that the host computer is doing some computation. And we can do offloads as well. So we do the broadcast, we do the calculation of the partial errors, and then we do the reduction to get the complete total error. And that's all you're doing during training, is that over and over and over again for 24/7 for months and years in the Google data centers. So what can you do now with this really simple mapping that I just pointed to? Well, this is exascale capable, because we can just keep adding machines as much as we want. And it's basically a transform reduce. This is applicable, it's a general class of optimization, which includes neural networks, but also local linear regression, neural networks, Bayes, independent components analysis, a huge range of problems. So basically, that's why I have, in my classes, I teach from hello world to exascale in one slide, which is true, because you can run to exascale capable computation. Here's the scaling on Tax Stampede on Knight's Landing to 3,000 Knight's Landing devices. And as you can see with the arrow, it's basically a straight line. You get kind of a little turbo lag in here as you start bringing in more and more switches, but then the performance basically flattens out. And you get the same thing for both linear problems, principal components, and a nonlinear principal components analysis. So this applies for both linear and nonlinear problems. Really exciting, very general. So here you hopefully see the path to exascale at the 13 petaflops. Give us enough compute hardware and we'll run it in exaflop. I always stress report honest flops, include communications overhead and everything when you're reporting results. So now we've talked a little bit about the mapping and a little bit about GPUs with that single instruction multiple data kind of mapping. And what GPUs do is they work on data in a data parallel fashion, and which is really great for feedforward and recurrent artificial neural networks. And so CPUs naturally handle task parallelism due to their multiple instruction, multiple data kind of an architecture. In other words, they can be running different instructions on different data at the same time. That's what happens in each of the cores. Not so much on a GPU processing core, which is called an SMX processor on the GPU. So you have to do some extra work, but you can actually get and do task parallelism. And here we see an actual perfect trapezes where it's starting out different tasks on a NVIDIA GPU. So now you see the big difference distinction between single instruction, multiple data, and multiple instruction, multiple data, and task and data parallelism. Really quick fire hose, kind of a traversal through those subjects, but they're important. So now let's go and take a look at why neural networks are so important. And I love this example. This was first done by Terry Sinowski in the 1980s. He actually ran this for a couple weeks on a VAX 780, but then he took a tape recorder and he could play this. And this is a way that he conveyed to people how powerful neural networks were. And it's, if you look at not just what's presented, but how he presented it, it shows how you can encapsulate a really complex idea in a very simple presentation. So what we have is a neural network architecture, which is basically a hidden layer network with two input neurons. There's some sort of a G function, which is a sigmoid. It saturates on both ends. And then there's an output neuron. So David Rumhart showed that this is an exclusive OR problem. And from that, basically, we can infer that neural networks are computational universal devices, because basically with these simple little logic kind of configurations, we can essentially have the network learn to wire itself up to perform each of the basic logic units that are used to build digital computers, general purpose ones. And so by extension, at least theoretically, a neural network could, in theory at least, wire itself up to solve any computable problem, hence it's computational universal. Networks without that hidden unit right here cannot learn the XOR problem, so they cannot represent a computational universal problem. That's why perceptron is not as powerful as a neural network. So to show the power of this, Terry Sinowski said, let's teach a computer network how to read aloud. Okay? Complicated problem. It takes people years to do that, right? So what he did is he ran it partway through and he stopped it partway through so you could hear the progress that the network is doing. If you can hear that. Was that, could people hear that? The kind of gibbering? Okay, great. Then he ran it to actually a decent minimum, and here's what you get.
I like to go to my grandmother's house, because she gave us candy.
So imagine that you're sitting in a room and a guy is using a tape recorder, because we didn't have PowerPoints back then. And he's showing you that by running on a machine from a training set, the network was able to learn to read aloud. The cool part is that you can show the network words it had never seen before that were not in the original training set, and it would pronounce them correctly, which means it had generalized a solution to the problem of reading English text aloud. Really powerful. We went through all that discussion of computational universality. In one quick demonstration, Terry Sinowski showed the real power of these neural networks, which is why we're using them again today. So Alan and I, of course, being opportunistic, we said, well, we'll do the same trick, but we'll teach it to predict coding regions. And we actually ended up forming a computational drug discovery company, which I'll tell you about in a little bit. So we've now talked about SIMD programming a little bit. And where's my pointer again? On both, and this is applicable to both vector and GPU hardware. And what I try and do is advocate to make your life simple. Start with the highest level programming interface first, which is using pragmas, like OpenMP4. And there's a beautiful pragma called SIMD, or ACC, which is actually designed based on SIMD programming. And then when you need more functionality or performance, go down to the lower level APIs. Okay? So, we've talked about now how powerful machine learning is and the potential in the technology. So what do the industry experts say? Well, Ian Bach is the head of the data center group at NVIDIA. He says in the near future, basically every piece of data in the data center is going to be interacted with by AI. Diane Bryant, actually, who's the VP for the data center group at Intel, made this very precise. She said by 2020, we anticipate the service will be running data analytics more than any other workload, which means between 2017 and 2020, there's going to be a huge ramp up in the use of machine learning technology, both for training and also for inference. So anybody who's interested in making money, this is kind of an interesting area. Anybody who's interested in making a name for themselves in science, this is kind of an interesting area. You do have the capability to make an impact and to change the world. So, the whole point of that is expect significant algorithm and hardware retooling over the next few years. And here's some more stats. Only 7% of all servers are being used for machine learning, and only a tenth of those percent are running deep neural networks. However, we've all heard the buzz about how important this is. By 2020, expect those numbers to go to 100%. So we've got basically four camps: the CPU camp, the GPU camp. There's something called field programmable gate arrays, FPGAs, and chips. I'm sorry, I'm not meaning to ignore y'all. I'm just looking over my slides so I can follow what I'm talking about. So we've got roughly four different camps. So let's take a look at the different camps. There's the NVIDIA GPUs, and they're the ones who restarted massive data parallels. Remember the kind of comic graphic? Once you do all your training on the Simul8, then NVIDIA's came out with something called the NVIDIA P4 and P40, which is essentially geared towards inferencing workloads. So once you train, then the payload, you don't get paid any money for training, basically. You get paid money for running inferencing that is able to do human-level tasks, okay? So inferencing, these are the GPUs that are designed to do inferencing in a very dense rack kind of an environment if need be. So why are GPUs considered so important in this area? Well, they have a very beautiful simplification. Is that basically GPU threads are grouped into something called a thread block. How many of you have heard what a thread block is before? Show hands. Not me. Okay. So a thread block is basically just some number of threads, and only threads within that thread block can communicate with each other. That's the simplification, and that's the beauty of the GPU computational model. Yes, there are atomic operations for those who are pedantic, but let's skip that for the moment. So we've got a thread block with some number of threads in it. Why is this important? Well, it gives us Fast hardware scheduling, because blocks can run only when all the data dependencies are satisfied. Remember, all of these are just, this block is running one single instruction, but has multiple data dependencies. Each one of these different blocks are the same way. So what happens is the data goes in, the dependency gets satisfied, and then we have a whole bunch of these things that go into an active queue. They're all sitting there, and we have this big, massively parallel GPU sitting over here. And so what happens is that the thread block goes in, and anytime a processor block is ready to run, it goes over there, and then the device becomes busy, and we start running. And then when you run out of thread blocks, it starts becoming idle. Okay, makes sense? And this is where we get to the part of the show. No, not yet. Where so the point is that executables can run unchanged on bigger GPUs. You don't even have to recompile, because basically you've already broken all the work up in the thread blocks, and you're just running on a bigger hardware platform. So it's a dealer kind of analogy. And so you've got a scheduler, and you've got one SNX processor. It raises its hand, said, "I'm ready for a thread block." You give them. Well, if I've got 3 of them, gee, all 3 of them plus the original guy get one. If I've got a whole room full of thread blocks, I can start spewing thread blocks as fast as I can deal cards. Okay? So that's why GPUs have something that I call the scaling execution model. And I actually do a little dance. In fact, there's a student. Oh, that's a dance. Actually do a dance in classrooms to kind of highlight for students that this is an important concept about GPUs. And it's a bit of wisdom from one of my professors at the University of Chicago, Jack Cowan. He told me that when he's giving a lecture, about halfway through the class, he has to tell a joke where the undergraduates will fall asleep. If it's graduate students, it's about every 15 minutes, and if it's alumni, it's every 5. So, we're now back into marketing, as NVIDIA claims that there's a big performance increase since 2013. 65x for training and inferencing 40x, okay? Big jumps. And they've been talking about something called reduced precision in here, which I'll get into a little bit later. But with the reduced precision, basically, that's good for only certain types of inferencing workloads. Turns out that speech recognition is an important workload. It's a niche workload, but it's an important one. So if we look at from 2013, that's basically, look at the growth that's going on in the number of essentially voice-related commands that are used, that are reported by Google Search. That's because everybody and his brother and sister are using their mobile phones and saying, where's the nearest pizza parlor? Google, tell me how to get to Greg Scantlen's place so I can buy a Stella 8. Or Simul8, sorry. You know, all those different things. See, you buy me a plane ticket, I say nice things. So basically, NVIDIA wants to put themselves as a position for inferencing workloads, which is a driving force in ubiquitous inferencing. Remember how we had the industry luminaries saying this is going to become a major workload by 2020? Well, that's not too far away. So here's NVIDIA's benchmarks on speech recognition and showing the Baidu Deep Speech 2 network. Remember that simple network I showed you before? Well, we're starting to get in deep neural networks where you have many, many layers. That's where the word deep comes from, because you've got many layers. And NVIDIA, not surprisingly, showing really good performance, in part due to the reduced precision. And the story plays well as far as reduced precision, because currently Intel processors power over 97% of the servers that are deployed to support machine learning workloads. That's always hard for me to say, I'm not sure why. And fewer than 3% of all the servers deployed for machine learning last year used a GPU. But if you look, NVIDIA stock is at a record high, in part because of their penetration of the data center. So if they continue doing that with the inferencing workloads, the stock's going to continue doing wonderful things for investors. Okay? So now we've talked about NVIDIA, let's talk a little bit about Intel. So basically that's processor-based computing. It's more of a standard vector parallel approach. And you've got a lot of different things. The key point is that with the traditional vector instruction set architecture is that you have a processing core sitting out there, and everybody in their cell phone and laptop has multiple cores on the processor, okay? And if we look at an illustration, those cores can have a vector unit on it of various widths. And what happens is the core issues an instruction, which is a vector instruction, and we start packing vector pipelines. And so that's why on Knight's Landing, you have to use multiple cores in the hyperthreading to keep the vector unit fully loaded. And in fact, on Knight's Knight's Landing, they actually have two vector units per core. That's how they get the vector units up so high. They also have some latencies as the queue fills up and the queue is empty. Okay? So that is actually the programming model for CPUs. Okay? This puts more work on the programmer, because the programmer has to both think in terms of making their processing code run with greater and greater parallelism, but also for each one of those threads that run on the different processing cores, they also have to be issuing vector instructions to get up to here. So instead of that one simplification, like with what GPUs did, with the traditional model, it's more legacy-based. There's a huge dependence on the compiler to actually generate the vector instructions for you. Okay? So, Knight's Landing, big improvements over the previous generation's Knight's Core. And the biggie here is that the double precision, and there's some fast memory. But as we move on into the Knight's Landing instruction set, the biggie is 4 threads, so greater parallelism for simultaneous multi-threading. And the other biggie is that there's the, sorry, my slides are a little out of order. Also, there's a higher memory bandwidth inside there. Meanwhile, Intel's also came out with the Purley microarchitecture, which is the Skylake processor family, which is the Intel Xeon processors. Okay, they've got 2 different processor families. And the nice thing is that this provides better memory bandwidth. And I'm sorry, I don't care what any vendor tells you. Most HPC programs nowadays are memory bandwidth limited. So it's really great if you can have lots and lots of floating point overhead. The bottom line is it boils down to any well-written program that you're going to be memory bandwidth limited. So the memory subsystem is going to be key for your performance. And also for the memory bandwidth, in this case for the traditional vector instruction architecture, we've got these wider vector instructions so they can do more floating point operations in parallel. That's how they get to the higher floating point rates to compete with GPUs. Okay, 4x capacity, memory, and also there's something coming out called 3D crosspoint, which I'm claiming is going to change dramatically computer architectures as we know it, because this is a non-volatile memory capability that can give you 60 terabytes of memory. In fact, I'll talk about some IBM results in a minute that are a bellwether of this, because they've got some really great performance from the CAPI in the open power configuration. But anyways, also what's nice about the Intel architecture is that you've got 8 sockets now instead of 4, so you can get 8 times the performance of a single processor. And so you're up to 448 cores, and basically on machine learning on a Broadwell, I can get a teraflop sustained. On Skylake, I assume I'm going to get 2 teraflops sustained. That's out of a 2-socket set. And so if we go to 4, it's going to be, or 8 sockets, it's going to be 4x that, and that's going to be a really nice performance boost. So we're talking about CPUs now that are well established into what is currently considered GPU teraflop performance regimes. And those are coming out now. And meanwhile, on-chip networking with Intel, they did something really right with Intel OmniPath. They have silicon photonics on the chip package. So the network connector is actually on the chip package. And that dramatically drops the cost of the network. And given that nowadays the cost, that can be 1/3 the price of the cluster, if you can decrease the cost of the interconnect and the network fabric, that means that you have more money to put into compute, which is the payload that's used for cloud computing and also for your institutional computing. Okay, just like training is not the moneymaker for machine learning, on network fabrics for transporting data is also not the moneymaker for the data center. So Knight's Mill is coming out. We talked about variable precision arithmetic as well. Everybody's jumping in on bandwidth on that, including AMD, just because you can get into the inferencing workloads. So what we've seen then is there's the different approach, Intel versus NVIDIA. And Intel has been following kind of a more balanced computing approach. And you can look at my article, which is called HPC Balanced and Common Sense, to understand what I mean by balanced computing methodology. But basically, the flops need to balance the memory bandwidth, because if you have too many flops and not enough memory bandwidth, those flops get starved because they can't get data. Meanwhile, if you don't have enough flops with too much memory bandwidth, which was the case in the 80s, then you can just saturate the floating point units and you don't get any greater performance. So that's one example, same thing with network bandwidth, et cetera, and we come up with something called a cadet diagram. So NVIDIA is using accelerators, and they've had great success with that. And they had 5 miracles that came through in coming up with the Pascal microarchitecture. And I'm assuming we're going to hear about some wonderful news at the new GTC, next GTC about Volta. So a key point now that we're learning for machine learning is that equivalently optimized software is essential. The key data packages that people use, there are basically 4 data packages that most data scientists use unless they work with a more high-performance custom platform like the one we do. But those packages are Piano, Caffe, Google TensorFlow, and then a middleware package called Torch. And by the way, these slides are available for people to download, so you don't have to take pictures. And feel free to ask any questions as much as you want. So I'm very lucky that I've got a good relationship with NVIDIA and with Intel, and happily with IBM as well as Cavium and some of the other companies. And unfortunately, NVIDIA is not real happy with me because I'm not publishing articles showing that Intel Xeon processors are actually beating GPUs for deep learning workloads, which creates openings for Greg's product as well. And the reason is memory bandwidth. Basically, we need to be able to pop around and supply the computational units with enough data. With the optimized packages, now we're actually seeing speedups where Xeon processors are matching GPU performance, previous generation, of course. And there's hope for the future for the nice landing offense. So what it boils down to is that, and here's another example showing your old talk too. It's more done by Colfax International. So what we're seeing at this point is that CPUs and GPUs are now kind of becoming really competitive against each other. What's coming down with the future? Well, there's custom chips, the ASICs. So here I'll talk about the Nirvana chip a little bit, which has a claimed 10x increase in training speed. The claim is they'll have the world's fastest deep learning platform for the foreseeable future. The reason is with a custom designed chip, there's no power being spent in trying to provide a general purpose computing functionality. The program is literally hardwired into the chip. And so as long as you get enough configurability to deal with the neural network architecture, it's very possible that a Nirvana chip could achieve those goals for a specific set of problems, because no CPU or no GPU can compete from a power performance ratio. And then we'll see how they price these things, that they can compete from a price performance ratio as well. There's other ASICs out there as well. Google has one, the Google TPU. Those are actually operating in the Google data center. So if you're interested in deep learning, you may actually be doing a lot of your work on ASICs somewhere in the near future by that 2020 timeline. Okay? Also, there's a number of other startups as well. FPGAs, field programmable gate arrays. I saw an Intel system, Intel bought Altera, which is an FPGA provider. I saw an Altera Stratus X FPGA running deep learning at the performance of an NVIDIA Maxwell generation GPU. Okay, so the FPGAs are coming along. However, the way I described FPGAs is the way a friend of mine described it once, is that with a general purpose computing architecture, when something breaks, there are people in the hallways yelling and screaming. With an FPGA-based project, when something works, there are people in the hallways yelling and screaming. They're really, really hard to program. So what's happening is that the software is now becoming recognized as a key portion of machine learning and other HPC applications. So my guess is with the acquisition of the FPGA companies that we're going to start seeing some libraries that will be coming out. And I'll note that the Skylake architecture processors have FPGA interfaces on them, which also tie nicely into the ASICs. Because I can keep talking for hours and hours and hours. So you know, and laughing at my jokes. Okay, so the reason why, so they're difficult to program. It's a nascent technology. It has the same advantages as ASICs in that you're not programming and building a general purpose processing unit. Instead, you can pretty much hardwire it. Where the advantage and where FPGAs are going to have to come in is they're going to fill the middle role because they've got power performance that is extraordinary. And the GPU guys are worried about that right now. but they're also more programmable. So as computer scientists start experimenting and coming up with new architectures and approaches that have faster convergence, better predictability, etc., that's where FPGAs are going to start playing a more important role in the data center because they're not hardwired like ASICs. And so that gives them the opportunity, data scientists, the opportunity to experiment with the high performance approaches that they want. They can then be turned into ASICs. Meanwhile, this starting ground, the proving ground, will be CPUs and GPUs. So Diane Bryant kind of summarized this at the Intel Development Forum in 2016. The FPGAs coupled with Intel's Xeon processor can deliver a significant efficiency boost. So Intel, her bottom line is Intel's doing things right. Okay. Well, NVIDIA also is looking at FPGAs, and right now they're showing that the GPU has better speed up and better throughput. But this is kind of the indicator for the future. Is the interconsumption need for convolutional neural networks, those are the networks that are used for identifying images, classifying images at better than human accuracy, is about the same. And so is the performance density. So we're going to see a real free-for-all coming in as far as architectures, which is great because competition means that there's going to be opportunity for pricing and at the benefit of the consumer. So as I mentioned, the common software packages basically are Piano, TensorFlow, Torch, and Caffe. There's a couple other. NVIDIA has a proprietary CUDA DNN for deep learning network library, and Intel DAL. Intel just came out with the data analytics library, which actually is very interesting because they recognize that they actually manage the data for you. Because data layout, remember memory data with this game? They actually manage the data layout so they can actually transform it correctly for the particular type of architecture that they're working. So that's, I like that approach that's in there. But most people are using Caffe, Torch, TensorFlow, Piano. So as long as you've got the appropriate interface in there to run your hardware with those packages, you're going to have data scientists running on them. Which is why I'm disappointed that AMD does not have any efforts at the moment to actually do that on the new hardware. AMD traditionally has great hardware that's hampered by rather poor software. And I won't say my real thoughts. So, as I mentioned, 3D Crosspoint. This is a non-volatile memory and storage. So we've talked about training and inferencing. But remember, the best way that I can phrase this is Alan Peters and I did a paper called How Neural Networks Work. It's easy to find. But basically we showed that what the neural network is doing is it's fitting a bumpy multidimensional surface. So if I look at my piece of paper and I've got bumps in here, I've got to have some data at every one of those points of inflection. If it's a complex surface, that means I have to have lots of data to represent all those different points of inflection, which is why training is a big data problem. Self-driving cars, lots of bumps, hopefully not actually a real road. So, what's happening then is that we have to come up with that lots and lots of data. So the point about the reduced precision, and I actually talked with the chief scientist at Baidu about this, is that you're trying to fit the surface. Well, how many of you have seen Minecraft? Hopefully everybody raises their hand, or at least everybody's not asleep. So basically what you're doing is you're kind of coarse grading that surface that you're fitting, or what your network can do, can use for approximating that surface. And so that's why reduced precision does okay for some problems, but not for all problems. And that's why it's a niche kind of an application, and you can't use it according to my preliminary results for training. So the other side of the coin is big data, is that actually generating and creating the data set can be as big a computational problem as the training problem itself. Because you've got all sorts of issues with data cleansing, clean data, getting data from unstructured sources and that, which is why a non-volatile storage technology like 3D Crosspoint that can run at 5 to 7 times the speed of conventional NAND flash, but it can also be tied in directly to the CPU to augment the memory capacity of the CPU. So with the Intel Xeon Phi, I go into more detail on this, but they have mirror memory, which is a stacked memory. And then they have the farm memory, which is the DDR4 memory. And then they can have an even slower memory tier, which is sitting out, which I don't know what they're going to call it, but that's essentially where 3D Crosspoint will fit in there, and then you get the storage. And so Do I have that here? Oh boy. I'll have to say that point for when I get to the IBM discussion. So let's move on to network cloud. Sorry for the disconnect there. So today, network fabric represents about 20 to 30% of the cluster's cost. As we move forward to higher bandwidth network connects, that's 30 to 40%. So that's why the on-chip optical interconnects are really important from the price performance view. And that's why I like OmniPath. And some of the architecture seems to be showing that it is a good interconnect to look at. The interconnect is very important for machine learning, not from a bandwidth perspective. If you remember way back to the early part of the talk, remember when I started talking about the cube graphic, the hands going down in the strong scaling execution model, you only do the broadcast of the data once. So bandwidth is not that big a deal. Where you spend all your time in training is doing that reduction. And that means that your latency dependent. People spend a lot of money on high performance interconnects to reduce the latency. If you've got an optical interconnect that has its own dedicated bus inside, that's going to beat the heck out of anything else as far as latency. And I've actually had, from my media connections, I actually interviewed the entire team in Russia that's actually doing the work for Intel, and they've got some really nice work that they're doing on reducing latency on that. And of course, latency is important because with the big data, remember finding those data for every point of inflection. That means that the computational problem becomes too big for any single computer, so you have to scale out to large numbers of computers, which is why, aside from just the big numbers, I was jumping up and down saying you can actually go to 13 petaflops average sustained training performance. Okay, so we can go with bigger and bigger and bigger data, and we can scale as we need to, which is why those scaling curves, although they're not 100% straight lines, it's pretty close to it. That's why those are so important to machine learning. Hopefully, I've closed the loop on that for you all. So, what I hope I've done is pointed out that there's a lot of confusion that's going to be happening over the next 3 years. Write your code once and run everywhere. As they say with Java, write once, profile everywhere. So that's kind of what OpenACC does, is it's designed to give you portability. Here's an example of C, Fortran, and C++ code. And I've actually seen PGI generate binaries and run the same code on an NVIDIA GPU and an AMD GPU, Intel Xeon Phi, Intel Xeon processor, and even ARM. And my guess is that at some point it could be even potentially FPGA. So the idea is to write your code once and run everywhere, which is why here's my from Hello World exascale slide, is that basically you have a little Hello World program. There's Hello World. And what you want to do is you want to load some data in, which is that init. And then what you do is you call that optimize method. Remember that black box optimize method, the gray area in that plot I showed you? And here's a simple least mean squares error function of some function of interest, my function, okay? And so that's sitting on my Intel processor, and I can have another Intel processor here, and I use the OpenMP parallel pragma right up there. And I can run in parallel across all the cores, and that's great. Thing is also I can do the same thing by adding in an OpenACC data load and an OpenACC pragma, and so there's the data movement with the OpenACC pragma, and then you can see in the yellow the OpenACC pragma running on the GPU. And now PGI is releasing an OpenACC version of their OpenACC compilers where you don't even have to have the OpenMP pragmas anymore. They run on multi-core and on GPU. So that's the whole reason why we came up with the OpenACC book. I was very lucky to work with a stellar cast of friends, because basically the history of the book is that after I wrote my first book, my publisher said, "Why don't you write another one?" I said, "Well, I'm working with this stuff called OpenACC." And unfortunately, the standard wasn't there, so the project languished for about 3 years. So at Supercomputing last year, in 2015, I was like, "Todd, I don't think I have time to do this anymore." And he said the exact wrong thing. He said, "We feel that we've chosen the right person to write this book. We have confidence in you." So I ran around SC, which is a great place to network, and I corralled all my friends and said, "Would you please write a chapter for the book?" And actually, we got a really wonderful set of contributions. So the first part of the book is staged so that the first third of the book is for beginners. The second part is for intermediate students, and the last one is for PhD and expert users. So the IBM approach, and what I like to do is use Simul8 HPC's quote, which is, fundamentally, accelerators are the path forward. And this is my friend Simul8. And they use these accelerators for compute, which is NVIDIA GPUs, and storage accelerators for big data, which is the OpenCAPI. And I'm going to tell you some rather fun stuff about that in just a second. IBM also kind of has Watson, the Jeopardy fame, the software. And then one of the most exciting things coming down, which is not a near term, but it's coming down the road, is the True North chips that are part of the DARPA Synapse program. And 40 billion synaptic interconnects using 7 milliwatts. You can connect one of those chips, it's basically a deep ring on a chip. You can connect one of those to the battery, and it would continue thinking until a battery just died from old age. You'd never drain the battery. So let's talk about that a little bit, because that's one of the futures. So one of the, I hope I included that on that. Anyways, so we're talking about True North now. I hope I didn't take that database slide out. I'm stealing my own thunder. So Jan LeCun came up and said, well, you know, this is an integrated fire type of neural network architecture, a little different than what we usually consider as a feed-forward or recurrent neural network architecture. It's more modeled on what the brain actually does. We do integrated fire neurons biologically. And he said, well, nobody's ever solved a real problem with them, you know, with any sort of accuracy. And so what IBM researchers did is they just published in August Proceedings of the National Academy of Science paper showing that these CNNs could be implemented on that particular E-brain on a chip at 70 milliwatts. And they could do between 1,200 and 2,600 frames per second, between 25 and 275 milliwatts. Milliwatts, okay? And effectively 6,000 frames per second per watt, which is extraordinary. The image recognition was competitive with the best state-of-the-art methods right now. So this is a sign that this technology is something that can change the world completely. So if you're interested in collaborating, this is from Tech Enablement. We tell you how to get there. Tech Enablement is my website. And here's the True North results showing the accuracy of different networks and performing inference on the different data sets and kind of the results from there. Just showing it's just not architecture, but this is why the paper got accepted with the National Academy of Science. This is a technology to look at. If I can jump up and down. In part because you can build really big, power-efficient neural networks. So remember I told you about a V-brain on the chip? How about a rat brain on a table? That has the same neural capacity as a rat brain. Okay? Notice there's no big power cables running that sucker. Okay, so if you're interested in machine learning, this is something to look forward to. Yep, I took out the slide because I thought it'd be too short on time. So one thing I do want to say is that for the data processing, remember how I was talking about you getting data from unstructured data sets? Well, that's where database type of operations become critical. And IBM has an OpenCAPI interface that they tied up for a financial benchmark called the Spec M3 benchmark. And they created a 60 terabyte main memory node, 60 terabytes, okay? And then they submitted, then they ran the Spec M3 database benchmarks. And the spec organization came back, and I had this I'm tied in with the spec org, and so I got the email saying, these are the fastest results we've seen reported to date. Some of the results, some of the runs ran 212 times faster than the fastest previous reported results. So the OpenCAPI storage accelerator is very exciting by itself, and also IBM's going to be looking at competition from Intel with the 3D Crosspoint, because that's going to be starting to fit in with main memory and also as part of the Skylake processor. So if you're considering doing big data, essentially you can do huge database problems, think terabytes of main memory, not gigabytes, terabytes of main memory, without having to resort to out-of-core methods. And then you can train and scale out. For example, if you talk to me, I can use my teaching code to show you, which you can freely download, and that's the code that I actually used to run to achieve 13 petaflops on the Oak Ridge Titan supercomputer. Of course, there's more to it than the teaching code, but that'll get you started. So you can think big. So if you think like Linus Torvalds, he got one of the first virtual memory microcomputers out from IBM, a PC, And it's like, I don't understand this virtual memory stuff, so I'm going to write my own little operating system. He did that, put the release out, and suddenly it took off, and Lemstorm also, without argument, changed the world. He did that as a student in the dorm room in Finland. And guess what? Everybody here can buy a teraflop plus capable GPU for $100, and even less from eBay. And you can start doing these machine learning workloads using any of these packages or mine downloaded. And you too can change the world in your garage, in your dorm room, wherever it is, because you have access to new technology. When I was a staff scientist in the theoretical division at Los Alamos in around '99, I had to write a tremendous grant and beg and plead and pray trying to get to run on the world's first teraflop supercomputer. Okay, that same computing technology can now happen on a $100 GPU, or at least the potential with the performance. So think of it as that you've got the potential to do that. Then learn how to write and learn how to speak.
And you have the Machine Learning Society to support you and bring some people together.
Absolutely. And the future is incredible. I mean, for myself, I've benefited from machine learning. My second company that achieved a liquidity event was actually a computational drug discovery company. And I didn't, I thought I included the slides in here, but I abbreviated it. Like I said, this is a 2-hour talk that I cut down. That's where I go into the algorithms. But basically, we were able to take real data, predict binding affinity, and do a hill climbing method on it. And we were able to actually then start designing drugs, compounds that would have tight binding affinity for particular receptor sites. Do the same thing with manufacturing optimization. With pigments, you can even do prediction of time series as well. So when I was doing my computational drug discovery, I set my sights high. I wanted to design a bot that if you got sick and you went to the doctor and you had pancreatic cancer, cold or the flu, doctor would take a tissue sample, whatever, put it in the box, which would go and click, and come back and essentially synthesize the same response that your body would. And he would give you a shot or whatever, and bye-bye pancreatic cancer or whatever, without the side effects. And that's a potential with this technology, with machine learning technology, because you can do custom tailored medicine. I mean, I talked about a huge number of other things. A project we did with optical coherent tomography, diagnosing retinal problems, and we did that using a GPU that cost less than $100. We were able to reconstruct the vasculature of the retina. I was asked by Tristan actually to do kind of a look ahead, and what do I think are kind of the problems to focus on. My big interest right now is, aside from firing and Greg neurons, which I didn't think of when I was talking to you, but recurrent neural networks. So that's where in feed-forward networks, all the connections go forward and the data flow goes from essentially bottom to top, to use my diagram. With recurrent neural networks, you have connections that go backwards. And the cool thing about that is that you can have memory then. You can have information persist across multiple evocations. So think of the power that you suddenly have with a machine that can learn algorithms that also has memory, okay? The other area where I'm very excited is the computing technology. When I did my computational drug discovery company, we used a Spark station and a connection machine. The Spark station that I did most of the work was about as powerful as this device I'm holding in my hand right now in the 93 timeframe. So we now have the computational capability to deal with multi-term optimization. What I mean by that is you have two terms. One might be strength, one might be weight. And you have a value that you change the importance of one relative to the other. So if you're designing for an airplane, weight is critical. So you want to make sure that you have a low weight, but you've got to get enough structural strength. Meanwhile, if you're designing for a truck, it's not so important. Same thing in operations that I'm talking about. So recurrent neural networks and multi-term optimizations. And I'll leave you with, I've got so many good stories. I'll leave you with one cautionary tale, is that with deep learning, when this came out, this is actually the resurgence of this technology. We actually saw it die because people promised so much and didn't deliver, and the funding agencies basically said in the late 90s, mid-90s, we're not going to fund these kind of projects anymore. And it wasn't until Jeff Hinton and others showed that you could do actual face recognition and deep learning that actually did a resurgence. And I'm going, yay, my work is important again. Get invited to talk to different places. But back in the early days, the guys at San Diego said, oh, we can use this. they did deep learning back then too. It's not a new thing. But they wanted to have a neural network trained up to recognize a tank versus a car. And you know what? It did really, really well. And then they took it out into the field and it did really, really bad. So they looked into the problem and finally they came to the realization. First off, my editorializing is this is not a human system. It doesn't have our assumptions. It's just trying to optimize the energy function. If it can set everything to 0, it will, and be very happy, and you won't be. When they actually looked at the data, they realized that all the pictures of the tank in general were taken on sunny days, and all the pictures of the car in general were taken on cloudy days. So the network was happily saying, it's a cloudy day. Meanwhile, boom, your car just got blown up. Too bad. I have tons of stories. I have probably exceeded my time. Y'all have been very gracious in staying and listening to me. Do you have any questions? I have so much fun talking about this stuff. So,
Yeah, why don't we do a question and answer session? I'm going to get the microphone, and anyone who has a question, raise your hand. I'll bring you the microphone. Any questions?
Uh-oh, he was nodding yes to many things I was saying, so this is a hard question.
Hi, I'm Mark from NVIDIA, so thank you for saying so many nice things about it. I just wanted to point out that you said 5 teraflops, that's for FP64.
That's FP64. Cool, thank you.
That's all, I just...
You guys keep bumping up the numbers.
Have questions. So
You keep bumping up the numbers. I'm gonna keep it. So what is it going to be for Volta?
They don't even tell us, but there will be some really cool things at GTC.
Yeah, it will be fun. And the nice thing is, Volta, I understand, has HBM2, which is going to increase the memory bandwidth, so there's going to be all sorts of wonderfulness.
And I just want to say that IBM is a great partner, that the CAPI interface have tiered memory, like you said, going from CPU to have a GPU that usually has 32 gigs or 16 or 12, now could conceivably have 2 terabyte just in stages further down the road. That's really
I'm excited. Everybody's real sensitive about benchmarks results right now, so I'm careful with that. But on Greg's system, which has, by the way, the NVLink on there, I did record the fastest machine learning benchmarks for the in-memory small parameter networks that I've seen to date, and that are smart. I was cleared by NVIDIA to say that I broke 60% of it. So, right, so that's good. You can get high performance.
Hi, thank you to both of you for wonderful talks. One question I'd be curious to hear your thoughts about. When you talk about these technologies for hobbyists, a lot of times one factor is when it shows up in the cloud, when it becomes easy to access, by buying a little piece of it. I'm curious if you think that Xeon Phi and downloads these other solutions will be showing up on Amazon, or whether some of the smaller cloud providers can sneak in there and grow by catering to people that want this kind of HPC capacity. If you're not a supercomputing center and it doesn't show up in your building, where do you see these things migrating to the cloud? I mean, GPU I can jump on Amazon right now. Xeon Phi is a different story.
Okay, so there's actually a couple aspects to the question that I'd like to address. So as hobbyists, you can start with a $100 GPU, and then you can scale out to a couple of them if your problem gets interesting. And then if you want to actually pull together a proof of concept for investors, you can actually move out to the cloud, because both NVIDIA and AMD have instances running on everything from the Alibaba Cloud to AWS to Google Cloud to a bunch of, yeah, all of them, and many of them are provisioned by Bright. So kind of the workflow that I'm showing is that you can change the world just by starting with one simple investment, which is not even an investment, you play games on it, and then move out beyond that to a cloud environment and get the results that you need to bring in investors. And that's a whole part of the talk I left out, is how we actually ended up getting money for the machine learning drug discovery company. I had to take out everything related to algorithms, or I'd have here until midnight. So that answers the first part of your question that I wanted to, with my own spin on it, is that, yeah, you can change the world with it. As far as migrating technology into the clouds, everybody's getting technology in the cloud. I mean, if you're running on the cloud, you're running on Xeon processors. You might have AWS instances using GPUs. NVIDIA actually gave me a real nice quote that The AWS CTO said that's the fastest growing instance they've ever seen in their history. And so there's real good stuff happening with GPU and CPU. As long as you have access to the software and either you do your own or you use like the commons for deep learning, which I'll point of my talk, so I'll focus on that, is Cafe, Theano, TensorFlow, and the Torch middleware, because there's a lot of R and Python stuff that resides on that, which is probably how you're going to get started to begin with, because all of it's free, it's open source, and then it's whatever platform that you have to run on. That's the second way to get kind of portability across platforms, is just using one package and you know, see and pray that everybody's brother different platforms. That's also where you're probably going to see the first ASICs coming in, especially on Google TensorFlow, the Google TensorFlow ASIC. Nirvana has their own software that you can run on CPUs now, but it's important to say that it will run on the ASICs when it comes out, but it depends on if you want to tie your horse to that, tie your part to that.
And the Xeon Phi, essentially Xeon, am I finding?
If you're running on Xeon, you really are running on Xeon Phi. The difference is the differences are becoming less important between Xeon layer, Xeon product family, and the Knights Landing and the Knights Mill. The real difference is that the Xeon processors are not as power efficient, which means that you can get away with doing a lot of stuff in the sequential portion of the code, because we're all fighting Anvil's law, or we're all addressing Anvil's law. So you got serial section code and you got parallel section code. So however you parallelize it, it's that SIMD architecture. It's going to run great on vector, and it's going to run great on GPU. Sorry, I guess I just lost the vote of confidence. But so then the question then becomes, how do you deal with sequential portions of the code? Intel Xeons are great for sequential code. They also burn a lot of power doing it. So Intel Xeon Phi is where the Intel designers are tweaking it down so that they can get to the exascale capable systems in a reasonable power budget. So the current Intel Xeon Phi processor cores actually run at about a third the performance of the Xeon cores. So if you want to avoid the pain of trying to make your code run more parallel, that's why people stay with Xeon. And that's probably going to happen for 2 more generations, is my guess. And then everybody's going to be forced, just like they had to be forced to go to multi-core to drop to low power cores. So you can probably keep doing what you're doing for about another 6 years, and then you're going to have to bite the bullet. That's my projection.
A few more questions, and also if you're interested in learning about the cloud, we have an event next Thursday at the Stanford Consortium for Regenerative Medicine. It's Google, Oracle, Edico Genome, and human longevity, and they're going to be talking about next generation sequencing, data analysis in the cloud. That's a free event, so I invite you to come and join us. And yeah, so, oh, and one more announcement. This has become a little bit of a culture here. This is the DOT, the Database of Talent, and the Machine Learning Society. We encourage all of our members to submit their resumes. We collect them and leave them at every event so that interested employers among you can look through it. We have an online version as well. Right now, the binder is about, I would say, maybe 40 pages, but we expect 400, 1,000. And again, for the Data Science Career Fair, we need more people getting involved. So if you're looking for work, certainly submit to the DOT. You'll see it on the website mlsociety.com. And if you're looking for people to hire, for talent, I certainly encourage you to come and take a look at this binder. You'll find wonderful members here that are within the audience and across the entire community of about 1,300 people. So lots of talent there. Any more questions?
Go for it. Also, while he's walking over there, I wasn't sure if there would be kind of a hands-on session, but here's instructions if you want to try OpenACC. Is basically you can download the free community edition, which is a high-quality PGI compiler that compiles for both CPUs and GPUs, and I believe it also compiles for power as well. So you can try it on all the different platforms. Collected great for running on power. And then what you can do is you can load the parallel programming with OpenACC GitHub repository from the book. There it is. And then you try the different examples so that you can actually get your hands on without any cost. And all you need is either a power or an x86 processor. No GPU required, but if you got one, we'll work on that too. So your question, sorry.
No problem. In your experience, what
would be the worst problem that you could give to a neural network or machine learning? What is something that is an example on something that it doesn't work on?
Oh, there's tons of them. If I wanted to be funny, I could tell you about the time we tried to predict the price of gold. That's one that didn't work. But actually, I will tell you that since I got a good laugh. Since we developed this technology, we thought, hey, let's use it for something to predict the price of gold. And darn it, we didn't do good. And we thought, well, we're going to put our own money into this thing. Let's figure out what it's actually doing. We realized it was using one neuron. It was saying the price of gold tomorrow is what the price of gold is today. Since we were looking at an upward trend, we were going to make money. If gold took a downward trend, uh-oh,